Hey there, and welcome. Today, we're pulling back the curtain on a process that is seriously everywhere, but almost completely invisible. It's the secret weapon behind everything from your morning juice concentrate to life-saving medicines. So let's dive into the amazing hidden world of industrial evaporation. It all really starts with a simple question. You've seen those frozen cans of orange juice concentrate, right? But have you ever stopped to think, how on earth do they get all that water out without just cooking the juice and ruining the flavor? Well, the answer is a really brilliant piece of engineering. At its heart, evaporation is something we see every single day. Think about a puddle drying up on a sunny day, or steam rising from a hot coffee. It's just a liquid turning into a gas, leaving behind a more concentrated version of whatever was mixed in. Sounds simple enough, right? Well, things get a lot more complicated when you try to do this on an industrial scale. We're not talking about one little puddle here. We're talking about processing millions of tons of product. So the huge challenge becomes, how do you evaporate that much water without using an absolutely staggering and super expensive amount of energy? To solve that problem, engineers have basically built up a whole toolbox of specialized equipment. Because, just like you wouldn't use a hammer to turn a screw, you can't use the same evaporator for, say, milk as you would for salt water. So let's take a peek inside the evaporator's toolbox. So, the most basic design is just an open kettle. Seriously, it's like a giant pot on a massive stove. It's cheap, it's simple, but its energy efficiency, it's terrible. So the first big upgrade was the tube evaporator. In this design, steam runs through a whole bundle of tubes to heat the liquid that's surrounding them. This gives you way more surface area for the heat to transfer, making the whole thing much more efficient and letting it run nonstop. And from there, the tools get even more specialized. So for delicate, heat-sensitive stuff like fruit juice, you might use what's called a falling film evaporator. The juice flows down the tube walls in this super thin, gentle film, so it evaporates really fast with very little heat contact. But what if you have a thick, goopy liquid that doesn't flow well? Well, then you need the opposite, a forced circulation evaporator, which literally uses a powerful pump to shove the material through the system. And for the really, really tough jobs, we're talking things like rubber latex or gelatin, you gotta bring in the heavy machinery. An agitated film evaporator has these internal blades that are constantly spinning, spreading the thick liquid into a turbulent film to maximize that heat transfer. It's incredible. But then, on the complete other end of the spectrum, you have the original method, open-pan solar evaporator. It's the ancient way of just letting the sun do all the work, a technique we still use today to get salt from seawater. Okay, so we've got all these amazing specialized tools, but that still doesn't totally solve that core problem of using massive amounts of energy. And that's where we get to the real masterstroke, the absolute genius idea in evaporation engineering, reusing heat to squeeze every last bit of value out of your energy. So here's the thing you have to understand. A basic single evaporator is unbelievably wasteful. You pump in a ton of heat to turn water into steam. That steam carries the water away, and then all that heat energy just vanishes into the air. It's kind of like using a whole tank of gas to drive your car around the block. Just poof, gone. So here's a look at how that wasteful process actually works. Step 1, hot steam comes in to heat everything up. Step 2, the liquid inside starts to boil. And then step 3, the vapor that's created just leaves. It just vents out, taking all of that valuable heat energy with it. And that is the problem that needed a brilliant solution. And the solution, it's captured perfectly right here. In multiple effect evaporators, this heat is recovered and reused. This one single idea completely changed the game for industrial concentration. So how does it work? It's actually genius in its simplicity. You use fresh steam to heat the first evaporator. They call it an effect. But then, the waste vapor from that first effect gets piped over to heat a second one, which is kept at a lower pressure. And then the vapor from the second one heats a third one, and so on. You're using the same heat over and over again. And what does that actually get you? Well, check this out. By linking just 3 of these evaporators together, you can evaporate roughly 3 times the amount of water using pretty much the same amount of steam you would have used for just one. You're getting 3 times the work for the price of one. I mean, that's a massive, massive leap in efficiency. But of course, even with this brilliant energy-saving trick, it's not always smooth sailing. Engineers still face this whole gauntlet of practical challenges when they're trying to concentrate different kinds of materials. It turns out it's about a lot more than just saving energy. Yeah, there are plenty of hurdles. Some liquids, like skim milk, have a tendency to foam up, and you can actually lose your product in that foam. Or minerals can build up on the heating surfaces.
It's just like that lime scale you get in your kettle at home, and that just kills your efficiency. We've already talked about heat-sensitive stuff getting ruined, and there's even this weird thing called boiling point rise, where a liquid gets so concentrated that it actually needs more heat to boil, which fights the very thing you're trying to do.
To really see how engineers tackle these problems, let's zoom in on one especially tricky category: biological materials. And this is a huge one. It covers everything from our food and juices to life-saving pharmaceuticals. So for these products, the name of the game is preservation. The amount of damage or degradation really comes down to just two things: how hot does it get, and for how long does it stay that hot? The entire goal is to keep both of those things as low as possible. So how do they do it? It's all about being gentle. First, they often run the evaporators under a vacuum. When you lower the pressure, you also lower the boiling point, which means they can remove water at a much cooler, safer temperature. Second, they use those specialized designs we talked about, like the falling film evaporator, to make sure the product is only heated for a very, very short time. And finally, the equipment itself has to be designed so it's super easy to clean, because you can't risk any bacterial growth. And when you put all of this incredible technology together, you start to see its impact absolutely everywhere. This isn't some obscure little process. It's a cornerstone of the food industry, for everything from juice and milk to sugar. It's absolutely essential in the chemical and pharmaceutical industries, and it's even a key part of how we treat wastewater, helping us purify and reclaim our water. So from the simplest pot on a stove to these complex, multi-stage vacuum systems, the engineering of evaporation is this hidden marvel that really shapes our modern world. It gives us our food, our medicines, and clean water. But even with all these amazing innovations, it's still a very energy-hungry process. And that leaves us with one last big question. What's the next great idea that's going to make it even smarter?